Hi everyone, my name is River Fiedler and this is my presentation on bisphenol A, also known as BPA, degradation using bacteria. I would like to give a shout out to my co-researchers, Emma Conge and Maria Gonzalez Bermudez, for all their work they did in the beginning of the project and helping me get to where I am today. So this is a slight overview of the presentation today. Uh, There's a main question. We'll be going over preliminary research, methods, results, conclusion, and acknowledgements. So for the main question, this whole project started with one question, and that question was, is there a way to have a certain bacteria degrade BPA over time in solution? You might ask, why is BPA degradation important? Well, there's a number of reasons. Some of them are, so BPA is a carcinogen, meaning that it can cause cancer. It's a hormone disruptor, so it can actually mimic estrogen, which can develop problems and issues. And then it's also a development disruptor, so it can disrupt development in fetuses, babies, and children. So why BPA? BPA is pretty much found everywhere. It's a known organic synthetic compound. It can be found in plastic containers, shopping bags, and most man-made plastics. And it can also be found in canned goods. And you might ask why cans? Because they're made out of metal. They're not plastic. Well, actually, canned goods have a plastic liner inside or under the lid, and that can contain BPA. So going over the preliminary research, the main goal is to find a bacteria to degrade BPA. But we didn't have a bacteria chosen yet. We didn't know. So there was a lot of literature research that we had to do. A lot of reading. Just reading what the other papers were saying and what they were doing and what they found. So many viable bacteria were found, but we ended up choosing Serratia marcescens as the bacteria for our research. So, why did we choose Serratia marcescens? Well, there's a number of reasons. One, it was the cheapest. It was readily available, so you could buy it on the internet. It was non-toxic, so it could be easily sent through the mail with no issues. And, in the papers and the literature that we looked through, it actually had a reported BPA degradation rate of 59.3%. And although that seems kind of low, but that was actually the highest of, not the highest, but it was among the highest of the different bacteria that were in the literature. So a little bit about Serratia marcescens. It's a gram-negative bacteria. It's known by its red or pink colony color due to production of protogeosin, and it is known for playing a role in about 1 to 2% of respiratory and urinary tract infections. And you can look at the picture on the bottom left, and you could also notice that it's got a very deep, red color, colony color. And what I thought was really cool when I was researching Serratia marcescens, I found on the internet that it is found in your bathroom or your shower or your toilet. So if you ever see like a pink residue in your shower or your toilet, that's Serratia marcescens growing there. So I thought that was really cool. So the next step in the project was creating BPA standards. So that was part of the method development, learning how to analyze it on the HPLC. So the goal was to research or develop a method to place bacteria in solution with BPA, grow over time, and then analyze the BPA degradation on HPLC. That was the ultimate goal. So to start with that, BPA standards were prepared by dissolving solid BPA in methanol and diluting it with water. So they were analyzed on the HPLC using a fluorescence detector, and this is shown in figure 1 below. So going back to the last slide, when we were dissolving the solid BPA in methanol, that was a bit interesting because in some of the papers they actually mentioned that they would heat the BPA in water and they were able to dissolve it. So we tried doing that first and that wasn't really working. So then reading some more literature, they actually used BPA in methanol and that the methanol helped dissolve the BPA. So we eventually started, dissolving the BPA in methanol first and then diluting it with deionized water to make our standards. So the next step was, dealing with the bacteria and methanol. So the bacteria tolerance to methanol had to be tested before growths could be performed. So, and this was another interesting step of the project that took a while. First experiments were done to determine the lowest percentage of methanol that could be used to completely dissolve the solid BPA without it crashing out. So going back to the last slide that I was talking about. So for a 200 ppm BPA stock with a final volume of 100 milliliters, 5% methanol to dissolve the BPA was successful. 2.5, 1.25%, and 0.625%. Those were all successful. So above 5%, that's a little bit too much for the bacteria to handle. So we tested 10% methanol with the bacteria and it did not grow. So that's why we chose like 5% and lower. So even though they were all successful, to make measurements and math easier, we decided to use 1% methanol in the 200 ppm stock of BPA. So, and this was also done to allow the bacteria to grow, whereas an increased amount of methanol did not allow the bacteria to thrive. So next, growth samples were prepared with a known amount of bacteria, BPA, and methanol to keep the BPA in solution and all diluted with growth media and deionized water. So going back to what I mentioned before, how we had to keep the BPA in solution without it crashing out or becoming a solid again. Whenever we were making new samples, we always had to make sure that there was, a good the same amount of methanol in there to keep the BPA dissolved, but also low enough to where the bacteria could still thrive when being grown. So then after the growth samples were prepared and grown, 1 mil samples of each growth was taken before and after so we could analyze that on the HPLC. And then we plotted the results as figure 2 below as abundance versus time for the 100 ppm BPA growth sample. So as you can tell, the black line is the before growth and the red line is the after growth. And there's not too much difference there, but there is some difference in abundance of BPA. So to the results, the before and after analysis of the growths were done with 3 different concentrations of BPA. We did 100 ppm, 10 ppm, and 1 ppm. So, and if you look to the right at table 1, so for the 100 ppm before growth, that was around 360,000, and then the 100 ppm after growth was right around 337,000. So there's a difference in peak area from the before and after. So, and then the same thing with the 10 ppm and 1 ppm. And then below, it can be seen that the peak area is decreased before and after the growth. So doing a little bit of calculations, the 100 ppm decreased by 6.1%, the 10 ppm decreased by 12.5%, and the 1 ppm decreased by 4.6%. So the BPA concentration, was going down for sure, and that's because of degradation. So to the conclusion, while this data indicates that Serratia marcescens is degrading BPA, replication of this data has been challenging and still needs to be done. So the goal is to recreate this data and try to expand on that, trying to get a better degradation rate, even though we got between like 4 and 12% for, you know, without those three, within those three samples. So some future steps include troubleshooting the HPLC method to achieve better baseline, using acetonitrile as the mobile phase instead of methanol. Some of the papers, some of the literature actually stated that they use acetonitrile instead of methanol. The reason we used methanol was because it was a bit cheaper and it was more available in the lab. Acetonitrile might be easier to use for separation of the samples. And then once the results are replicated, the next step, as I mentioned before, will be to determine how to increase the percentage of BPA degradation, because that's the ultimate goal. And then finally, my acknowledgements. I would like to personally thank Radford University Chemistry Department, specifically Mrs. Gilly, Dr. Balia, Dr. Monceau, Dr. Stefaniak, and Dr. Burkhart for all their extended help and knowledge along the way. And I would also like to thank Dr. Kennedy, my research advisor, for her continued support and guidance. Thank you very much, and I hope you guys have a great day.